So welcome to the FEM at Livermore seminar. We've been running this since the start of the year, and as long as we keep getting quality folks to come in here and present, we'll keep doing it. Hoping to do it next year. Before we start, I wanted to mention to everyone that we do have the MFEM Community Workshop coming up in October. So if you have not received an invite for that, you can go ahead and find an invite for it at mfem.org. So if you're interested, please go ahead and sign up. We are taking speakers for that as well. So if you have something you want to present at that, we'd be happy to have you there as well. But right now, we are in the seminar series, and I'd like to introduce Dennis Ogiermann. He's an applied computer scientist from Germany, University of Bochum, with strong interests in mathematical modeling and numerical simulations of a broad range of phenomenon in life science. He wants to deepen understanding about living matter as well as improving diagnostic treatment of diseases. He did his bachelor's and master's at Ruhr University, Bochum, in applied computer science, and his doctoral position is also there at the chair of continuum mechanics, where he currently investigates numerical techniques to improve simulation bidirectionally coupled electromechanics simulations of the heart without compromising accuracy and the corresponding model validation on an organ scale. This project is in a tight cooperation with Assistant Professor Luigi Prodi, who is the head of computational biomechanics lab at the University of Central Florida. Further, he's the vice president of the local student chapter of the German Society of Applied Mathematics and Mechanics. So Dennis, why don't you go ahead and take it away? Looking forward to seeing this talk about cardiology.
Thanks for the nice introduction, Aaron. So let me straight head into the talk. First, I will give you a little overview about anatomical and physiological basics, so you can easier understand what we are modeling here. Then I will, in my first section, present about pure cardiac electrophysiological simulations, because they are rather hard to handle. Then I will head forward to the forward problem of electrocardiology, and finally give you a little overview about bidirectionally coupled electromechanics of the heart. As the first motivation, why do we want to model the heart and do computer simulations about it? First of all, cardiovascular diseases are the killer #1 worldwide, as we can see in the data from the World Health Organization. And also they impose a huge economic burden on us, since people usually don't directly die on heart disease, but slowly deteriorate. Now, our computer models can help us to gain insights about how the heart functions, and therefore we can also derive, for example, therapies from it or new diagnostic tools. Challenges here for cardiac simulations are primarily in the problem that we have multiple temporal and spatial scales involved, as for example seen in this overview given from Chabiniak. We have multiple physics involved. For example, we have the fluid dynamics, we have the electrophysiology, we have the mechanics. And finally, we also have large uncertainties due to the stochasticity of the heart. The slow scales are inherently stochastic, but also, for example, imaging procedures which are not invasive, like, for example, the MRI, usually give us highly noisy images of the heart. So the goal of my project is to develop a flexible computational environment to explore cardiac function. Let me first give you the overview about basic cardiac anatomy and cardiac function. The heart is basically a biological electromechanical pump, which pumps the blood through the body. As we see on the right on a sign MRI given by Luigi Perotti, who worked under Daniel Ennis' lab in Stanford when deriving this data. We are having a big heart chamber. We have different heart valves. we have a small heart chamber, the right ventricle, and we have some upper small chambers called the atria. In the basic cardiac cycle, blood flows into the right and left atria, are pushed to the ventricles, and the ventricles push the blood through the body. Now, what's also important is the microstructure of the heart. As we see on the left, we have some measured microstructure for the heart where we visualized the cardiac fibers with tractography, which has been derived from Krishnamurti's work from 2014. And generally, as we see on the left, the cardiac microstructure has some helical organization through the heart wall, as we see in the right on the schematic. And these helical fibers are also organized in sheetlets, giving you a pretty anisotropic structure, especially an autotropic structure, which will be important later. Now, the last important piece of cardiac function is how do we actually pump the blood? And this pumping function must be coordinated. For the coordination, we have the cardiac conduction system, which is like a wiring system through the heart, as we see on the right. We are having some pacemaker nodes named the sinoatrial node. We're having some fast fibers giving you electric currents over the ventricles to the atrioventricle node, which is the node between the atria and the ventricles. And finally, we have the Purkinje system feeding the wires into the large heart chambers. In the large heart chambers, we have this web, which is the Purkinje system, and its basic function is to coordinate the electric activation on which the cardiac pumping function follows. On the bottom, I have a small visualization of how the big heart chambers on the bottom activate. We are having some current going into the atrioventricular nodes through the Purkinje system, activating the ventricles in an almost homogeneous manner. Now, to cardiac electrophysiology. For the cardiac electrophysiology, we usually assume that we have a generalization of the cable theory, which is called the bidomain model. And in the basic cable model, we have three fields, namely the extracellular electrical potential, the intracellular electrical potential, and since we have a membrane, the cell membrane, separating the extracellular and intracellular space, we also can define a potential across the membrane, named the transmembrane potential. Now, both media, intracellular and extracellular, have some resistance, which give rise to some connectivity tensors when we move this model to 3D. And since we have the membrane comes with capacitance, because it does not allow charges to directly flow over the membrane. And we have some active holes in the membrane, named the ion channels, which can open and close due to different mechanisms. In the first part, we will focus on voltage-activated ion channels. And for these voltage-activated ion channels, we can write down the full bidomain equations as you see on the bottom. So we have some parabolic-like part, we have some elliptic-like part defined on the heart. And we have some state variables governing the dynamics of the ion channels, which is just dependent, which is non-linear function just dependent on the transmembrane potential and the state of each ion channel locally. Finally, we also have some boundary conditions, namely we do not allow the fluxes to flow outside of the intercellular extracellular space in the heart, if we think about the heart in isolation. And since we see we have this elliptic portion needs also some kind of anchor, which we define as a Dirichlet boundary condition, which is also named the grounding. So how do we treat this equations numerically? Basically, a very common scheme is the operator splitting scheme, for example, derived by Q and Garfinkel in 1999, where we have a splitting into a diffusion operator A and some reaction operator B. This way, we obtain a linear PDAE defined by M and A, and a nonlinear but pointwise system of ODEs named V, defined by M and B. So, for example, the first order Litrotov-Godunov scheme can be described by first solving the PDAE and then solving the nonlinear pointwise system of ODEs, where the second solve utilizes the solution of the first solve as an initial condition. We have also checked the consistency of this kind of scheme successfully with the Hydra benchmark. I will tell you later how we solve these ones exactly. So, first, for the electrophysiology, if we are just interested in wave propagation and not interested in extracellular fields, then we can take some simplifying assumptions to eliminate extracellular field and just have this nicer system of equations. We can treat them again with some operators Q scheme, making a reaction diffusion split again. And very characteristic for these so-called monodomain problems, since we just have one domain, which we solve for, is that we have very steep traveling waves, which travel very fast. So you see we are in the millisecond regime, and this is a few centimeters of cable onto which the wave travels. If we look at a single point, then the solution will look somewhat like this here. We have this steep first portion over the first milliseconds, and then some buckle. I also want to note that while we can, with this unphysiological assumption to derive a monodomain equation, we can also just assume that we have these equations and think about what is the error if I just take some arbitrary conductivity tensor here. And Coudier has shown in 2014 that the mean harmonic tensor choice for this one is also sufficient to get very similar solutions to the bidomain solution for physiological conductivities. And with physiological, I mean, we can't just take any conduction here, but the ones which we have derived from experiments. Now, with this class of PDEs, we get some very interesting pre-asymptotic behavior. Namely, if we think about discretizing the real number line with some continuous Gardner scheme and just define some bistable reaction for our ionic portion, namely we neglect the internal state variables of our ion channels and initiate a traveling wave, which we just let to travel indefinitely, then at some point the wave speed will stabilize and we can measure this wave speed. We can do this also numerically, and we know, as given in the Pizzuto paper, some exact wave speeds which we approach. And for not so super coarse discretization sizes of a real number line, we see that for either linear or quadratic or cubic or Hermite discretization basis functions, we get just linear convergence. So basically, if we reach this regime, we already have a solution which is sufficiently fine. This is in accordance to the boundary layer theory, which we, for example, know from fluid dynamics. Now, since we can't just scale up our order, which is what we initially wanted to do, we had to change our strategy towards an adaptive mesh refinement scheme. And here we utilize the Kelly error indicator to drive the error, the refinement process. And basically, we have a tree-based adaptive mesh refinement process, where we have a forest of elements where we can refine each element individually with a tree to track the refinement derefinement, for which we utilize the MFEM library. And the actual error indicator can be described as integrating over the boundary of each element and summing up the fluxes, especially the jump in the fluxes across the element. Because we know if we have a continuous Gaussian discretization and just take the derivative fields, we get an L2 field, which has actually jumps in the gradients and fluxes. So with some threshold-based scheme, we now can say, okay, if our error on an element is below some threshold, we refine it, and if it's above some threshold, we de-refine it, and we see that this strategy successfully is able to refine the mesh at the wavefront. We also assume that these kinds of estimates perform well based on the theory derived by Ratti, where this kind of estimate also appears. And we know this kind of estimate is pretty big in problems of cardiac electrophysiology from experience. Now to some more interesting cell models. We said that we have this state, which we want to evolve, associated to ion channels. And for example, for the PCG, canine ventricular calcimode model, we have 6 of these ion channels and a total of 6 dynamic ion channel states. A side note here, it is not directly associated that we have for each ion channel 1 gate, but each ion channel can possibly have multiple gates or no gate. The model has a total of 36 parameters, is fitted exclusively against canine data, which is pretty special. Usually, these kind of models use a mixture of different experimental data. The dynamics is physiologically plausible. It has some nice numerical properties, so no discontinuities on the right-hand side, nothing super steep. Okay, we have some steep variables, but nothing actually discontinuous. And it has undergone extensive uncertainty quantification and global sensitivity analysis. So being a pure Hodgkin-Huxley type formulation, we can write down the ionic currents as the sum over the ion channels, where we have for each ion channel a maximum conductivity, open probability for all ion channels located on the surface of our cell, and some battery potential. So this can be seen as ohmic current, as also seen on the right of the slide. For the evolution of these resistors, being a Hodgkin-Huxley type model, we can choose the right-hand side, G, as some nonlinear diagonal matrix function acting on S, and some vectorial function B. Details for how these look exactly can be found in the original paper from Hartmann. So to our first experiment, we have utilized this model, scaled up one of the conductivities, namely the TO conductivity, which is known to induce unstable spiral waves, as shown by lambda. And as an initial condition, we use the trick induced by Padmanabhan, where we have a gradient in the transmembrane potential and the fast gates. And we see on the bottom that this directly introduces a spiral wave. And due to the ion channel conductance, we also have very unstable spiral wave dynamics, which can be seen that usually you just have one stable rotor. If it gets unstable, we have this multiple rotors creating and extinguishing each other. We also see that the adaptive mesh refinement scheme here works very well, tracking the wavefront properly, but also getting our errors on the tails pretty low. For the adaptive mesh refinement simulation, we got a speed up of about 4 times only, which is due to that we have not properly optimized the code yet. Now towards the forward problem of electrocardiology. One of our goals is that we want to validate the heart model at organ level, so we can utilize it in the clinics. One of the important tools herefore is that we want to correctly reproduce ECG signals, so the electrocardiogram. Ideally, the ECG has 5 primary features: the P wave, corresponding to the activation of the atria, the QRS complex, corresponding to the initial activation of the large heart chambers, the ventricles, and some T wave corresponding to the repolarization of the ventricles. Some important features of the physiological ECG. So in the healthy case, we should not see any slurring or fractionation, so we have no kinks herein. We also have specific features for the QRS duration amplitude, so the width of this must be within some range, and also the amplitude. Then, depending on where we measure the ECG on the body, there is a very specific relation between the height of the peaks, and also the T wave should be positive with a longer rise and fall. This is a bit extreme. It's an actual ECG, not this extreme, but just here for visualization purposes. What are the challenges here? First, the conductivities of our tissue are basically unknown. I will show you later more about this because this is what I'm currently actively working on. The measurement of the conduction system is problematic because, especially in the clinical environment, we currently do not have the tools which have the requirement accuracy to measure this cardiac conduction system. Also, we have big uncertainty generally in the microstructure of the heart, namely the fiber direction, sheet direction, and the direction normal to it. But we have made huge progress recently, as for example seen in recent work by the Daniel Ennis lab from Stanford. Another problem is that these simulations are really computationally demanding. So simulating the full thorax with the heart electrically can take some time. And the ECG is also a quite sensitive measure, which is on the one side good, because if we mess up something in the model, we will definitely see it in the ECG. But also it makes, for example, fitting procedures really hard. So how do we model the ECG now? I already showed you the bidomain model, and now we also add some conductive medium around our heart, as seen on the top right, which we call the bidomain model with torso. So the red portion is our bidomain model, the blue portion is our Laplacian conductor bath. Technically, we could also deploy here Maxwellian formulations, but usually we don't do it, as we assume that the time development of the magnetic fields is negligible. To couple these two, we assume perfect transmission conditions between the extracellular potential and the body potential here on the outside. And generally speaking, in cardiac EP modeling, this kind of setup is the gold standard. So we don't have actually much better setups than this. Also, we want to note that most of the prominently used ECG models in literature can be identified as special cases of this model, as we have shown in previous work. And to get the ECG, we just need to evaluate our body potential at some specified point. So now to first experiments on the ECG. We take a transmural wedge, which is basically we have our heart and take out literally a wedge through the heart wall and do experiments on it. We embed our transmural wedge onto some conductive medium. We also model the microstructure with a rotating fiber distribution and assume that our bath is surrounded by some perfectly insulating boundary. Now what we see here on this slide is that I have taken from literature quite a bit of measured and theoretically derived conductivity tendencies. And we already see here that the measurements are quite different. So we see here on the bottom, if we measure in a simulation, activating this wedge here on the bottom, measuring the difference between the E4 and E3 electrode, that depending on the chosen conductivity tensor, we get very different results already in this very simple experiment. However, we see here dashed lines and the solid lines, where the solid line is the PCG model as shown before, and I have also chosen the TNP 2006 model as to compare against, and we see that the choice of the cell model is actually not so super important on the overall shape of this curve. So the direct ECG is quite sensitive to the conductivities, but the cell model can be chosen rather arbitrary as long as it's physiologically accurate. So if we utilize a toy model, then we cannot expect that these results look similar. Now we also realize that we are wasting quite a bit of computational time when we compute full ECGs. So we have proposed some adaptive time-stepping scheme named the reactant tangent controller for the bidomain problem with thorax. And it is based on some theoretical derivation from Spiteri and Siragari, where we know that the difference between the analytical solution and our numerical approximation for the operator splitting scheme can be bounded by 4 errors, namely the spatial discretization error, the splitting error coming from the fact that we have this exponential splitting, for example, the LTG splitting as shown before, some time-step error which we make by solving the diffusion problem, and some time-step error by solving the ionic subproblem, namely the cell model. The spatial error can be driven down either by having a superfine mesh or utilizing the adaptive mesh refinement. The time discretization error of the diffusion problem is usually negligible, and we can also bring down the time-step error for the ionic problem by utilizing special solvers for this one. For example, exponential or adaptive Euler schemes. We also know that the splitting error directly correlates, and it heavily correlates, with the L-infinity Bochner norm of our ionic current and our stimulus currents. So our proposal is to make the choice of next time step length as a function of this Bochner norm. And primarily, we have chosen the sigmoidal function to control the time step length. So is this reasonable? Yes. We see it on very simple experiments that if we measure at some material point the trajectory of our solution, that here on the solid and dashed lines, they cannot be distinguished. So the solid line is the reference solution, the dashed line is the approximation given with our RTC. And also for the internal variables, so in S, for example, we also have included now the calcium concentration and the troponin-bound calcium concentration, which are important, for example, when we couple our problem back to the mechanics, or if we investigate unstable spiral wave, for example, during fibrillation. Also in experiments on the full ventricles, when investigating the activation times with this scheme, we see on the top the reference activation times and repolarization times. Namely, we have used the ventricle here again, as shown before, activated on the interior, and check at which point in time the transmembrane potential is above some threshold. And for the repolarization time, we do the same, but we say the first time point after which it is below some threshold, again, after being activated. And we see for our adaptive scheme that we get some fancy patterns here. However, this is just some numerical noise, since the activation time here is in the order of 15 milliseconds, and the errors in the activation time of our adaptive scheme is about 0.05, 0.1 milliseconds, which can be neglected. Also for the reproduction times, we get another fancy pattern. And this pattern directly correlates by having jumps in the coefficients of the cell model, since we have in this experiment correctly tried to model the microstructure of the heart. And this assumes that we have some epicardial, endocardial, and mid-myocardial cell types, and also the same thing in the apicobasal, so top-down direction here. This can be seen as a generalization for operator splitting schemes of a scheme, for example, proposed by Whiteley in 2007. For the cell model, we use an adaptive Euler scheme proposed by Kuhn-Garfinkel. And what is very interesting about this is really simple to implement. We just have to control the next time step as a function of our Bochner norm for the ionic currents. We get about a factor of 10 times speed up for normal cardiac cycles. However, we also want to note that the scheme has just limited use, for example, in fibrillation studies, because we are controlling the time step length globally, depending on the activation of the tissue. But during fibrillations, usually the tissue is always somewhere activated. We also have more formal errors, namely the space-time errors again as Bochner norms, for example, L2, L2, L2H1, L-infinity L2. And we see in each of these measures that the error is very small. Now, going a step further, we also said that we have a cardiac conduction system, which is very important. And we want to introduce especially the Purkinje network, since we have here focused on the large ventricles, into the simulation. For this, we utilized algorithm proposed by Vergara, which is an iterative coupling scheme for the Purkinje network with cardiac tissue. We assume that we model the Purkinje network again with either a bidomain or monodomain model. And the algorithm is also rather simple. Instead of solving with the usual stimulus, we utilize a modified stimulus in the solve, where we have the normal stimulus, which we would anyway use, plus some correction term. Same for the EP problem on the Purkinje network. And we see in the schematic on the top right that we have this line, which is the Purkinje network. We have a block, which is the heart tissue, or a representative of a heart tissue. And we have some coupling regions at the end of the Purkinje network. And we couple basically this region here as a volume average gap voltage, also here. For the gap voltage, it is basically defined as the difference between the end of the Purkinje system with the volume averaged current in the heart in this overlap region, divided by some resistance, because actually we have in this coupling region some resistance, so the flow of the electric currents is not unlimited. And as long as two consecutive gap currents are not close enough to each other, we iterate the scheme. Vergara has shown in his paper that this criterion is sufficient for convergence, and that we always reach this convergence criterion with this type of scheme. And to also demonstrate how this looks, we have, for example, an activation here in the beginning of the Purkinje network. It travels across the branches and activates the block of cardiac tissue. Now we can forward and get to some real ECGs. Here we embedded again Krishnamurti's heart into some blocks-like structure, which is just embedding the heart into a water tank, for example, and place some electrodes around the heart, which emulates the measurement of the clinical electrodes. Here we show the Wilson leads. And on the bottom right, we see with this flocky-like pattern. This is actually the Purkinje system doing its work, activating the ventricles. And as streamlines, we see the current generated in this box for the heart. Now, why don't we use directly the full torso? Well, the full torso comes with additional uncertainties. For example, how exactly do we couple the torso with our heart? This is an open question in literature. And also we have organs which interact with the current generated here, which have additional uncertainties due to how is the conductivity of this tissue, what is a pictorial model, is the Laplacian conductor really a good approximation for the currents here. But we see already in this simple setup with different approaches, we can reproduce ECG signals in the VT, for example, V5 and V6 leads, which look reasonable. Now, the function of the heart is not to generate currents in our body, but to pump blood. So let us next take a look at the bidirectionally coupled electromechanics. First, I will give you a very short introduction in large deformation theory, because the mechanical motion of the heart during its pumping function is quite big. And basically, we have some undeformed configuration from which we start our contraction, for example, and some motion path for each material point in the undeformed configuration, which gets continuously mapped to some deformed body. We also have some helper sizes here, namely f, that f, and cofactor of f, and f is the so-called deformation gradient, which is a function of the gradient of our displacement field, where the displacement is just the difference between the undeformed and deformed configuration. Now, why is f important? F basically pushes lines between the reference configuration and the deformed configuration, which we will need later to push our fibers forward and backward, for example. And also, we have to define some kind of partial differential equation which we want to solve for to obtain our displacement fields. Here we assume that our first Piola-Kirchhoff stress tensor, P, can be obtained from a strain energy density function. This is the usual assumption which we have in, for example, hyperelasticity. And this is not a typo that I have written here, a partial derivative, but it is just a note that our strain energy density function can also be a function of different quantities than, or not only f. So we get as governing equations for the rest of the talk, ignoring the dynamics of the body, just the divergence of our stresses to be zero. Now to the active formulation of our mechanical heart tissue. We utilize the generalized field model as proposed by Göktepe in 2014, where we basically have on 1D an active spring, a passive spring in parallel, and the active spring interacts with the sarcomere. The sarcomere is basically the contractile unit, biologically and physiologically speaking, in the heart, or in cardiomyocytes to be specific. In this framework, we assume that we have a multiplicative split of our deformation gradient into an elastic and an active portion, and that each spring is associated with some potential energy, namely the passive and active potential energy. The active deformation gradient is a function of some microstructure given some active stretches, and the active stretches are then given by our contraction model. Now we define the fiber stretch. Note this is different than the active stretch. It has this quantity, and we can rewrite this quantity by pulling this f over to the other side, since this one is a scalar product, defining some tensor C. In C, we actually define our energies here. And we also have our CE, which is the same thing for our elastic deformation gradients. Now the passive and active, we assume, not we assume, but given this additive split of the energies, we have also an additive split of the stresses, where the passive stress is derived from some neo-Hookean type energy, and the active stress is derived from some linear spring type potential. The active stretch relation is taken from Pelzit, 1995, where the active stretch is basically just a function of the normalized intracellular calcium concentration. And finally, we also assume that each of our cells, given in the physiological regime, is incompressible. Now we have to modify our PCG-canine ventricular cyanide model to also incorporate the stretches and the calcium dynamics. And we have, for simplicity and for the sake of demonstration purposes in this talk, chosen a minimum calcium dynamics model and some very simple stretch-activated currents. We try to stay in the Hodgkin-Huxley framework, so we have Hodgkin-Huxley-like formulation. However, we had not found data from dog, so we use rat data to fit these ion channels. Again, this model is also in mind that it should be still simple to implement, so we can easily reproduce experiments here. Since part of the goal here is that we have some fully verified framework here, for which we can analyze our algorithms to speed up all these simulations. Now the ionic currents are now split up into what we had previously, so the voltage-gated ion channels, and now we have stretch-gated ion channels, ISAC-K and ISAC-NA, which are, as mentioned, derived from Nidra and Smith 2007, where we have, again, the maximal conductivity and some dependence on the stretch of the cell. So this is a Macaulay bracket. This can be roughly translated to if this quantity is below 0 or negative, then this whole term is negative. And otherwise, we just take whatever comes out of this term if it's positive. For the minimum calcium dynamics model, we have something affine in the transmembrane potential and the intracellular calcium concentration chosen. Now, how do we handle this one numerically? Basically, we have a two-level operator splitting scheme where we first make a physical split into the mechanical and electrophysiological portion. And then again, for the electrophysiological portion, we apply again the operator splitting scheme to get what I have described before. This way we get two PDEs and a nonlinear spatially decoupled system of ODEs again. This also allows us to deploy some multi-mesh type methods where we have different mechanical than the electrophysiological mesh, which allows us to easily incorporate the adaptive mesh refinement into the scheme. And the solution scheme is basically that for the time advancement between Tn and Tn plus 1, we first solve the mechanical subproblem, transfer the fiber stretch to the EP mesh, solve the EP problem, and transfer the calcium concentration from the cell model back to the mechanics mesh. And this concludes the time step. A note on the transfer of the fiber stretches. Would you remember the fiber stretch is directly dependent on the gradient of our displacements. So we have to do an L2 projection onto the mechanical mesh node before doing the interpolation from the mechanics mesh to the EP mesh. And also a note on how do we incorporate the rect tandem controller to make the time step length of the EP adaptive, since the time scale of the mechanical problem is much coarser than the time scale of the EP problem. We choose the delta T max and the RTC dependent on our time step length for the mechanical sub-problem to match the time discretized grid. Now, the first benchmark which we derived is again a modified version of the Nidra benchmark, where we electrically stimulate a wedge on one corner fix the displacement on one of the sides of the mesh, and utilize a modified PCG-driven model. As we see on the reference simulation and the space-time adaptive method, we have solutions which are visually basically indistinguishable. However, the reference simulation took about 7 hours, while our space-time adaptive method only took 2 minutes. For the reference simulation, we chose a small time step length to make everything properly converging, and also have a fine mesh for both the mechanics and the electrophysiology. So we do not deploy the multi-mesh method here, and no adaptive mesh refinement. We end up with a speed up of about 100 times. So to our final experiment, we also want to show that we can not only simulate these toy problems like the knee drawing wedge, but also simulate the electromechanics on real hearts. So we have chosen again Krishnamurti's rabbit heart, where we started with coarsening the mesh to make the adaptive mesh refinement somehow useful. We up-project the measured microstructure on this coarsened mesh. Again, we utilize the Purkinje network for activating the ventricles, and to make the solution well posed, we again have to fix the displacement on the most apical faces. Again, we see that some of the important features are already qualitatively well resolved with our proposed scheme. Namely, the conduction velocity is about right. What is not right here is still the choice of the conductivity tensors, which is ongoing work, and the wall thickening is also properly shown here. Unfortunately, the simulation took a bit longer than the wedge. Namely, it is about 1 hour of wall clock time, but it's still in the speed up order of 10 times against a fully non-adaptive scheme of a naive approach. So, to summarize, I have presented you a hierarchical operator splitting scheme for the electromechanical handling of cardiac models. I have also shown an adaptive mesh refinement scheme to speed up EP simulation, which is purely based on the Kelly error indicator. I have finally presented a time adaptive scheme to also speed up the temporal simulation of the EP problem with our new proposed reaction tangent controller, and we end up in most simulations with about 2 orders of magnitude speed up over the naive strategies. As future work, we also want to investigate the local adaptive mesh refinement schemes, since, for example, in population studies, we still want to utilize the different temporal scales, but the global adaptive scheme actually fails because it is global. We also want to incorporate more improved cell models with biophysiological accurate mechanical interaction, and develop a validated setup to simulate correct activation and motion in a very robust way. So overall, we want to have a fast and accurate four-chamber simulation environment. With this, I want to thank you all for your attention.
Thank you, Dennis. Everyone, we should give Dennis a round of applause. There's a button for clapping hands if you can find it. If anyone's got questions, I've got a couple I wanted to ask. Thanks for showing us all that. It's really quite a synthesis of a lot of models, and it really gives us a good idea of what it really takes to model these really complicated electrophysiological systems. One of the questions I had, so for the ECG modeling, you were trying to validate, up against, maybe real ECG measurements, or at least make it look kind of like the ECGs that you get. Is it so? But you've got these models where you've kind of got, your signal, and then you've got the body that you're going to be placing your ECG leads on. Bodies are so inhomogeneous. There's just so it seems like such a hopeless problem to me to really get a good
I
read
think
out of that, right? So
so.
like just the variation in conductivity across the different organs and stuff in the body. How can you account for any of that, or is it just you're within, you know, plus or minus, a factor of two or something like that?
If we look at the measured conductivities, for example, just for the heart tissue, then we already see that there is quite a bit of variance. So that's just an open question on what are the actual correct conductivities. And what this also raises the question is the bidomain model is actually already a correct choice, or if we need something more general. For example, we have the assumption that we neglect the Maxwellian interaction, for example, magnetic field. It's interesting to explore, but no one has done it yet because it will definitely be more expensive to simulate.
Yeah.
And regarding the organs, we have a full data set by Moss, and also Plonsey has mapped for multiple organs the conductivities. And in the Moss paper, they already come pretty close to correct ECG. However, this is just ECG. This does not tell us if the activation of the heart is also physiologically correct, because we have a mathematical model and we can just tune our power meters in a way that we get the correct ECG for the wrong reason. And that's why we try to develop an environment, especially with this tank experiment, to get something more robust. Getting this into clinics will be another beast, because then we also have a question if what's the variance between subjects. So does different patients have different conductivities of the heart tissue? How can we obtain it if it's different? And yeah.
Yeah. No, it's a very hard problem for sure. And it's you you're really trying to get these simulations together with so many unknowns, and just doing the best you can. One other question I had, so you're working very hard to keep this, the simulation time down, obviously. Um, what kinds of like are you already putting these on supercomputers and running them, or is this like a desktop setup? How much computing power are you using on these, and how much more could you do if you had more?
So actually, I can run both. I can run on clusters, but I can also run on my working station. All of the shown simulations are simulations with 16 cores on working station. So
Okay.
for example, the contracting heart here on the bottom, it took with 16 cores on MD Epic 3950 about 1 hour.
Okay.
Part of the problem is if we utilize the Kuhn-Garfinkel adaptive time stepping scheme, then the scaling completely breaks apart because some processes have the traveling wavefront, some doesn't, and the processes just have to wait until the processes which have a wavefront converge towards the solution.
Right, right. And have you had any luck using GPUs these days, or?
I tried, but the speed up is it's not worth it yet.
It's okay.
I mean, there are some groups, for example, the Hardware project, which put their solvers onto the GPU, but I think currently we are more having with the shown schemes a load balancing issue than actual compute issue. However, if we deploy the local time adaptivity schemes, for example, the Runge-Kutta discontinuous scaling schemes, then we can think about again the GPUs. And also another reason why GPUs are may not have too much. In the solvers for the diffusion problem, I usually just take like 6, 7, 9, 10 iterations, and the CPU can handle this. But it was also the plan that I deploy GPUs, but it just turned out that it doesn't work so super as with high order, because it looks like it's a really great fit for high order, but when you turn up the order and it's just not what you expect.
Right, right. So, does anyone else want to chime in with a question here? I'm kind of dominating the question space here. Well, I've got another one. So, say, could you actually? It sounds like you've got this wavefront problem, so your scalability breaks down. Could you think you could use like a couple thousand processors if you
I mean,
or would the scaling just be so bad that you can't? It's no good.
Scaling already falls apart with 16 processors. You just
Yeah,
get a speed of 4 to 10, depending on the partitioning and stuff. So,
yeah,
everything gets just blocked. So, what I
yeah.
really try to push for is to get better um, um, rebalancing.
Hmm.
This is an open topic which I'm also working on, but I just couldn't find time to properly get everything together yet. Because if I utilize adaptive mesh refinement, which is rebalancing, things get a little better.
Yeah,
But it's still yeah, problematic.
yeah,
But it's not
yeah,
impossible to solve.
yeah, yeah. Well, excellent. If no one else has any more questions, maybe we'll go ahead and wrap it up. Why don't we go ahead and thank our speaker one more time? And
I also have to thank again for the invitation.
absolutely, it was really I'm really glad we could bring you out and see some of this excellent work. Again, it's a really solid synthesis of a lot of different kinds of models and putting them all together to really try and tackle a really hard problem. So I love seeing work like this, um, and I hope to see you and others at the upcoming workshop as well.
Sure.
So
MFEM already helps here to develop these schemes. Due to the modularity which we have, we can just test out things very quickly. It just
yeah.
takes usually a few hours to test something new.
Yeah, absolutely. Absolutely. All right. Well, thank you again, Dennis, and thank you all for showing up and for this seminar. We'll see you all again next month.